can be downloaded from ghidrasre.org. Again, today we'll be using version 9.04. So this is the Codebreaker Challenge resources page. You can go to the resources tab here. And again, we're going to be looking at the Windows binary from 2014. And if you want to get the solution from that year, you would download the 2015 Tech Talk. Again, looking at the other link, if you want to download Ghidra, version 9.04 is what's available right now. You can download it from ghidra-sre.org. And without further ado, we'll move on to the demonstration and take a look at the challenge. This is from the 2014 Tech Talk, the overview. We're going to solve tiers 1 and 2 because that's about all we have time for, and I think they are interesting, which is also one of the reasons why I selected this particular Codebreaker challenge. I think it's very accessible. You can make decent progress from the beginning and have done something interesting from binary reverse engineering. So task 1 is to determine how to execute the hidden functionality. So that's telling us there's some hidden features of this program. People are using it to communicate, but it looks like something else. So we need to figure out the right arguments and the right execution environment. So I already have it downloaded here in just September 18 demo in my documents folder. If we just ran the program, which is not always the best idea when you're dealing with unknown programs, but this is a toy developed by the NSA. We don't see much. It looks like a weather application. Sometimes you might just try a handful of random things. -H is often a way to get some help. And again, it doesn't really tell us much anything that we didn't already know. We can ask for versions and so on and so on. It doesn't, again, tell us much. So our really only option is to exhaust things endlessly and hope that we get lucky, or we can open it up in Ghidra and take a look and see if we can't find something. So here's the Ghidra front end. I've already got a project started. If you haven't done that before, it's just new project. I'm going to go straight to import file, and here's codebreaker2.exe. Let all the defaults do their thing. Just hit OK. And then when you double click on it, it'll pull it up in what we call the code browser tool, which has a lot of the core features of Ghidra. I'm going to let it do its auto analysis, leave all the defaults, and this thing will churn away for a bit. You can see the progress bar down in the bottom left, and it should only take, at least for this binary, about 30 seconds or so. It's doing, again, a lot of the typical basic analysis that you'd expect for a binary reverse engineering tool. It's identifying function starts, it's figuring out stack frames, locating global variables and strings, which are all going to be very useful for us to kind of get some traction into this problem. So you can go ahead and type questions now. I will address them later, but if you have them as you come along and you just want to get them out on the screen, you can do that, and I'll read them 15 minutes before the end of the presentation. All right. So strings is a good way to get some traction. So one of the things we can do is just look for some of the strings that are already printed by the program and try to find out where those are located in the application itself. So we could start with, weatherman help. To do that, we go to the defined strings table. This will display all the strings that Ghidra has already found, and we can just type into the search box, weatherman help, and it looks like the string is here. If we click on it in the table, it'll take us where that string is located in the actual binary. To give you a bit of an overview, binaries themselves are just a collection of bits and bytes here displayed in hexadecimal. So this is the raw data. One of the things that Ghidra will then do is disassemble those things, and that's what's in this middle panel here. And then we'll look later to see how Ghidra decompiles those. An interesting thing to point out is that the processor description language is very generic, so it's easy after learning a domain-specific language to add new processors to the system. And we've in fact gotten several contributions from internet users for new processors. And then the semantics of those instructions are encoded in what we call P code, which is an intermediate representation. And all of the analysis that Ghidra performs, including its decompilation, is built on that intermediate representation. So you can get a decompiler for an architecture pretty quickly by implementing that architecture in Ghidra. So we'll look at the decompiler once we get into an actual function. So one of the things Ghidra tracks are cross-references. So not only does it show you where that thing is in the application itself, right, where it's laid out, but it also tells you what things refer to this. And here we see there's a reference from a function called tier 1. That might be an indication that we need to go here to solve the tier 1 of the problem. And we can double click it to take us there. At this point, we can actually look at the decompilation. It's not very pretty at the moment for those who might be familiar with C, right? There's not much useful here, lots of pointer arithmetic and other sorts of nonsense. And while automated tools are quite powerful occasionally, they're inevitably going to come across something that causes them to stumble, and they need a little bit of help, and this happens to be one of those cases. For those who might know a little bit about reverse engineering, you'll notice that this function call appears in the middle of what would be the prologue of the function. It's still manipulating ESP here. So what this is telling us is that this function here might be being used to allocate memory on the stack. The Ghidra decompiler knows about this sorts of things, but sometimes it doesn't detect it automatically. We have to tell it a little bit about this function. So we'll say edit function, we'll tell it that we want to apply a fix-up, and this is an allocation probe, and we can hit OK. And now the decompiler will go through its rigmarole again, and this time it looks quite a bit better. We can in fact see the strings as it's using them. We can see where that string was being printed out to the screen. And then we start to see in the code, right, what this application was actually looking for and why it hid things from us. It appears it's checking to see if it can access a file called temp secrets in the C drive, and if it exists, it'll print this -X to enter a hidden mode. So that's interesting. It might tell us something that, well, let's see what happens if we just give -X to the program. It didn't really do much. It just tells us invalid setup, but we know that directory needs to exist, so why don't we just try making that directory, and then we'll try running the application again and see if we make it any further. And there you have it. We've completed tier 1 already just by doing a cursory examination of the source code that appeared in Ghidra's decompiler. Granted, that was a bit of a hiccup to tell it about that allocation probe. So let's move on to tier 2, and that'll be the last tier we solve as part of this demonstration before we move into questions. So let's go back and read what we're supposed to do for tier 2. It says, accessing the hidden functionality requires passing an authentication check. You can probably see that we've actually been presented with that authentication check here. To solve this challenge, you'll either need to find a way to bypass that check or get a correct set of credentials. Today, we're going to look at obtaining a correct set of credentials. So we can try putzing with the thing and just seeing what happens. If I type in Dan, it just says invalid username. So apparently there's some check on the username itself, and I'm not going to get too much further until I examine the code. So let's do a little bit of work naming some things in this function. One of the nice things about Ghidra is it's interactive. So you can type in the names of variables. You can retype, or I say retype, I mean like variable types, right? You can tell it's a char star and whatnot. And those things will inform the decompiler to help it display things better. And it's also just a good way to help you remember where things are, or if you're sharing your reverse engineering, the names of things are quite powerful. So one of the things we might notice first is, well, I mean, this VHLI is kind of interesting because those are the same things we saw, right? VHLI being asked for in the help. So there's a good chance that this thing is being used to process some arguments, and it's part of a while loop. So, having done this before and rehearsed it a bit, I'm going to call this next arg. As we can see, again, it seems to be doing a comparison and switching. On these cases, they're not displayed in the best way at the moment, but one of the nice things about Ghidra is that it has a built-in Python interpreter. Technically, it's Jython, but we can still use it to do, quick questions like, what is that character? Oh, that's capital X. That's, so it's given us a good idea of which bits of code are being used to process which arguments that come from the command line. So we might name this here that we saw flag X. We might name this here that we saw flag H. Again, we could name this that, secrets is present. And we could go on. We don't necessarily want to name every little thing in here because sometimes if you commit yourself to thoroughness, you'll never finish, right? So it's good to just kind of get the things that are useful and move on. One thing we might notice here, though, is that this flag is supposed to be for the L, but it also comes out as setting flag H to be true. So perhaps our first guess of what that variable was named wasn't quite correct. So we might try to find out what it's being used for. And here we see if flag H exit. So really this flag is saying that, we're done. And so we're going to exit afterward. And we can see that the other flags are setting this variable as well. So pretty much any flag except -x is going to cause the program to terminate before doing anything interesting. All right. So since we know where some of the exit is, we can skip past the rest of the arguments processing and move on to some of the next stuff. Here we noticed that it had been attempting to fetch some weather information from Yahoo. We can see that this is the code that's perhaps doing that. So can skip past most of this. We see where it's printing out the forecast, again, doing its actual fetching using curl, so not very interesting. And here again, we see it checking this temp secrets again. So perhaps we're getting back into some interesting parts of the code. We also see where it printed tier 1 of the challenge completed. So perhaps we could have just skipped right forward to here by using strings again. Here we see some stuff that's a little bit difficult to process. This is one of the unfortunate things currently about using Ghidra on x86 is that x86 is a complex instruction set computer. So some instructions have very complex semantics, and Ghirdra will unroll those semantics and display them to you. And so this instruction, which is normally just a repeated store, is being shown as a while loop, when really this is just, I think, mem copy or mem set. And it could have been displayed a bit easier. So things aren't perfect. We got lucky because it's checking that it's a directory. If we had made it just as a file, we would have gotten an invalid setup message again. But here now we see where we're at, enter username, and it's going to call fgetS, which is a well-known function from the C library. So I can name this variable username. I can also tell Ghidra by using Control-L what the type of this variable is. Right now it thinks that it's some undefined type of size 4, and there's 256 of those in an array, and it's probably because it saw it being initialized by that mem set in a strange way. So we can change this to be a character of 1024, multiplying by 4, because characters have a size of 1 byte, whereas undefined 4 has a size of 4 bytes. We can also see that this hex 400 is 1024 in decimal. That's telling fgetS what the maximum size of that buffer is. So we have the username variable named. It looks like this is seeking out the end of that username. In case it ends with 10, which is end of line, it's going to normalize that and change it to a null terminator. So we have the username with a null terminator at the end. No new line. And again, we see this complex instruction being used. It happens to be, in this case, it's strlen. And we get to the end of this block here where it's finished computing that length, and it's checking to see whether the length is less than 8. And that's where we got this invalid username message that we saw earlier. So perhaps the reason why I wasn't able to pass this check is that the username wasn't long enough. So let's try a longer username. And here we can see we've proceeded to the next step. So we still have to figure out a password that's going to be for this. Here we can see where we just got to. The application had printed out, so we can see in the code where that was being done. And this time, we see a similar call to fgetS. This time, the name of the variable, though, was going to be password. And again, the nice thing about naming the variable is that name propagates to everywhere else that variable name is used. So it's important to do this. And again, I'll give that a proper type of a character buffer of size 1024. And then here, we have a very tempting function name. So we can see it says get password from username. I would hope that anybody who's ever written a secure application knows this is not the way to do password checking. For real, you should be doing some hashing. But it looks like in this case, the application actually generates the password and then does a comparison to see if the expected password matches the password of the user. So we'll name this. We're kind of making a guess here, but it's a good chance that this is going to be an output buffer for the expected password. And again, we'll change the type of this thing to size 10, or to a character buffer of size 1024. You can double click on this function to navigate into it. The decompiler will do its magic again for us automatically. Excuse me. And we can start naming these parameters. Having seen how the function was used, we can know that this one was called the username. Maybe we want to encode that it was an input. So we'll say in username. It has a type of character pointer. Param2 is perhaps out password. This will be a good opportunity for us to verify that guess. And then we have param3, which if we went back to how it was called, just use the navigation panel up here. We can see again that it was that hard-coded size of 1024. So we can guess that this thing is the length of the buffer, or the size of the buffer, or the maximum size of the buffer. So here we can see some initialization. This time it actually shows up as a call to memset, where we initialize that output buffer to 0, and then we copy the username into that buffer. And then we start initializing some variables and doing some algorithm here. So all this algorithm is doing is perhaps generating a password. So we'll look to see exactly how it's doing that. So it seems to be reading in out password, but again, remember that the username was copied into there. So this is actually going to be the first character of the username that's being read. And we can see that variable is being used here as well and is getting the next character out of the password. So we can probably call this next in, meaning it's the next character in the password we're getting ready to process. We also see that this variable, I don't know why it's passed between this temporary thing in the meantime, but that's what gets copied to the out. And so this is the last thing that was copied out into the password buffer. And now we kind of have a decent idea of some of the names, and we can look and see what this function is doing. If we're curious what this value is in decimal, it's 95. And then we also have hex 20, which is 32. So this range may seem familiar to some, 32 to 127. Those are all the printable characters from the ASCII table. So this is basically ensuring that whatever password it generates can actually be typed out on the keyboard. So let's actually duplicate this algorithm so we can generate our own password for the username that we just punched in. So I'm going to go ahead and get started in Notepad++. I'm going to save this into my demo directory just as SOL for solution .py. And I'm going to start converting this C function into Python. So we can say get password from username. And we'll just go ahead and initialize that last out variable. And we'll also initialize a buffer to store our password. And because next in is just iterating over the password, there's a fancier Pythonic way of doing that, if you will. We'll just say, I want every character in the password, and I'm going to address each one in sequence. So now we can look at translating this line over. Unfortunately, Python does distinguish between character types and integer types, so we're going to have to put those conversions in here explicitly, but we should be able to do it fairly straightforward. So we've translated everything up to the modulo operator, but I need to add in a set of parentheses to make sure I do the order of operations correctly. And then I can apply the modulo 5f plus x20, close the parenthesis, the whole thing should be now converted to a character. We'll go ahead and append that to the password buffer. That should be everything that's necessary in that loop. We'll return the password, and then we'll save this thing, and we're going to import it into the Python interpreter that I have in Ghidra. Now, granted, at the moment, I've not used this Python interpreter to do anything that you wouldn't be able to do with a normal Python interpreter, so you could just use the normal Python interpreter. But just to show that it can, this actually has access to the program database that's being displayed on screen right now, so you can do interactive scripting and everything, and interact with Ghidra programmatically through the Python interpreter here as well. Again, it's a bit of a waste because I'm not using it to do that today, but it's still convenient to have it around, and because I don't have vanilla Python installed on this system, I can just use this one. So I need to get that directory into my path. This is a bit of a nuisance, but I'm gonna normally, if you're developing scripts in using Ghidra's interface, it does this sort of stuff for you. But once I've done this, I should be able to import, nope, Maybe not, because I forgot the documents part of the directory. All right. So I'm going to import that function into the Python namespace, and now I can actually just invoke it. I used this as the username. And so now it's printed out what, if I've done my work correctly, should be the password that's necessary to unlock the application. So I'm going to go ahead and just copy this and then paste it. And there it is. We've completed tier 2 of the challenge. Again, I know this was a bit fast for a live demonstration, but hopefully you can look at the recording if you're interested in following along for the tutorial later. And again, hopefully it would provided some convincing that it's a quite powerful tool to either use as part of your own work or to make available in your courses. So with that, I'll go ahead and open it up for questions. How do I display the chat while I'm sharing my screen? Okay. Let me find out where the questions begin. Okay, as far as the release cycle is, we don't have a formal release cycle. We tried to aim for like every 3 months or so, but right now we're kind of preparing for our 9.1 release. So we've been very slow to get that out. Let's see. Do I know what makes Ghidra more or less effective than IDA? So I must admit I'm not deeply familiar with IDA and all the ins and outs between both of our tools. I will say one of the things that I believe we have as an advantage is the intermediate representation. And so that basically means if you can spec out a processor for Ghidra, you get decompilation and the rest of our analysis stack for the most part for free. Occasionally there's some weird nuances to a processor that you have to work out. Let's see. The A72 or other ARM architectures, we do have support for the ARM architecture. I don't know about that particular 72 that you've asked about. I can pull up the list, perhaps. I don't know if it's going to be big enough on the screen here, but I'll just say I want to re-import this thing, but I'll lie to it and say I would like to specify the language myself and don't show only the recommended ones. So this is a complete list of all the processors that are available in version 904. Again, we have our filter in here, so you can type ARM, and it looks like we have V7 and V8. So I assume that includes the 7.2 that you're asking about. Let's see. So all the documentation is actually available in the download package. Let me see if I can find it here for you. This may be an older version. Yeah, this is a bit of an older version than what I'm actually showing, but if you go into docs, Ghidra class, we have a lot of courseware available for it. You can start with beginner if you'd like, and then there's the student guide with notes, and there's also, actually, I don't know if that's there, but anyway, it's a bit weird because I've zoomed in a lot in the browser here, but these are basically just the PowerPoint slides for our courseware. Let me see. Let's see. So you can contact us on GitHub if you have either an idea or an issue. You can always submit tickets or participate in the forums in the wiki there. We are, taking pull requests and things. That's probably the best way to contact me or anybody else on the Ghidra team. So we do have some visualizations. This is a bit of an active area of research for us, but one of them is actually the function graph view, which if you do window function graph, this is all right here. And again, it's similar to what you probably would have expected. It has the listing and things available inside. Let me see if I can zoom in a bit here. But yeah, You can drag and customize these things. Another thing that's kind of interesting, which I just accidentally displayed, is that all the tools here are synchronized. So if you select something in one view, it is selected in the other view. If you move your cursor in those views, that's even true to some extent of the decompiler. If you highlight a block of code, it tries to show you what blocks of assembly code that's derived from. This is, if you ask me, an insanely useful tool for teaching the connection between high-level languages and low-level languages. So again, I think that's a good reason to incorporate it into even just a basic course on computer organization and assembly. All right, let's see. From a curricular perspective, where do you see Ghidra feeding in and teaching reversing concepts? Do I still think there's value in teaching them how to read assembly? Yeah, I mean, I guess I've not experimented with it much myself. I usually try to emphasize teaching the connection between low level and high level before I perhaps go straight into the tools. Right, I'll start with obj dump, right, just as a means of showing what assembly code looks like for those who've not seen it before, and try to show, say, how to recover a control flow graph by hand. And then maybe after having done that, I wouldn't spend too much time on that before introducing the tool. And again, your experience may vary depending on the aptitude of the students you're working with, and every class is going to be a little bit different. If you find out somebody has relied so much on the tool that they're not understanding what's going on behind the scenes, usually that comes out later. Hopefully it's not too late, and you can remediate it sooner than later. But I think this one does a decent job of showing that connection as well. Even having access to a tool like this, it can be very tempting, right, to just say, well, I don't need this stuff. You spend all your time over here, but that can be rife with disaster. Let's see. Thanks for an awesome tool. Oh, you're welcome. I'm glad you all like it. Are there sample binaries? We don't publish any of those from the Ghidra team, but the NSA does have a few challenges out there. The Codebreaker challenge, which I demonstrated today, is probably one of the better resources if you want, binaries that we've put out there. We've put a couple of videos out online, just how to introduce and use the tool. There are a number of YouTubers out there who've put a bit together as well. So there's plenty of content that's actually not produced by us, but nevertheless, it's been pretty quality. And just for those who are curious, the Codebreaker Challenge this year is open. I think it just started, was it today? I don't know. If it wasn't today, it's starting very soon. And it goes through January 10th. This year, it's going to be dealing with Android applications, which Ghidra is capable of handling. So I hope you all get a chance to use this tool on a more interesting use case. Some of the more recent ones have involved, backend services and things which have made the problems more interesting as well. Whereas Codebreaker 2 didn't, which is one of the reasons why I selected it, because it's more accessible and doesn't depend on that. Is there a way to look at the P code? Yes. There's kind of two different ways of thinking of the P code. There's the actual specification itself, which is more C-like. I can try to show you what that more or less looks like. If you go into any of our processors directories, say I'll pull up the x86 under data languages. There's an ia.sync file. This stuff is all on GitHub as well. If you want to, make a contribution, you can see them in our source directory. They're basically just copied into the build. Let me see if I can copy this or drop this into Notepad++. And we'll try to make our way to something a little bit more interesting here. A lot of kind of just setting things up. Maybe I just can look up add. All right, so this one's not the best formatted, but you can kind of see that there's the more or less the C-like syntax for specifying this thing out, right? Add the immediate value into AL, and because this is, add AL immediate 8. So that's one view of it. If you're looking to develop processor specs or just understand what an instruction is doing, you can read the manual, but this is an alternative, way to see that. You can also see what the actual P code is for that compiled C-like syntax by pulling up these headers and enabling this P-code field here. And then you can actually see, excuse me, the intermediate representation, right? And in some sense, this is almost a lower level assembly language than the machine code that you're looking at, but it's designed so that the decompiler can kind of understand those primitives and piece together an approximation of the C code back out of it. So yes, you can view the P code in that way. Did I miss anybody's questions? Have I gotten them all so far?
I think you are good to go, Dan.
All right, thank you all for having me. I hope you enjoyed it.
Thank you so much for speaking today. So I just wanted to let everybody know that the recording is going to be available on the CAE community website. I've dropped the link into the chat box. It usually takes about 24 to 48 hours for us to get it on the site. So if you don't see it between now and then, that's why. As soon as it's available, you guys will be able to see it. So that's it. Thank you guys for joining us today.